Good afternoon, everybody. Thank you for joining today. We are very lucky to have the visit of Richard Goldfarb here in Johannesburg, and thank you for joining the GEOTALK. Richard Goldfarb is a consultant, and as he said, is old and he's been in the gold business for a very long time. And today he's going to speak to us about orogenic gold, the reality and the fiction. And these are very topical since we see all the communication that are coming out about the new model about the Wits. So thank you so much and enjoy.
Okay, thanks. We'll turn off the lights. I'll set my timer so I don't go for 2 days. Timer. Okay, that's better. Well, maybe I better hold one because I'm going to be looking at the screen and all right, well, I'll try this way. Anyway, what I want to do is really a talk in 2 parts. Talk to you in general what we know about orogenic gold or gold in metamorphic rocks today, and then move on and talk about the science fiction of it. There's so much garbage out there in the literature now. Everything gets published. And it's hard to know what is real and what is not, what you should believe, what you shouldn't believe. And I'll move on and talk about that later in the talk here. So if I can see the thing in the dark to move it, okay. You know, when we talk about gold deposits, gold deposit types, clearly the great paleoplacer here, South Africa, the Wits, was 1/3 of the gold ever known on this planet. But if we ignore the Wits for now, especially as we're very deep there and it's become less and less economic, the gold can be divided into 2 types of gold deposits that we explore for and mine on our planet. Gold deposits that are associated with intrusions, mostly oxidized intrusions. Those are our porphyries, our epithermal deposits, to a lesser extent, gold-bearing skarns. Those are shallow magmatic deposits associated with oxidized intrusions. The other half of the gold we explore for on this planet is orogenic gold or gold in metamorphic rocks. Now, just quickly, half of the gold, as I said, we're exploring for is shallow magmatic gold. And oxidized intrusions form gold deposits generally in the upper 3 kilometers of the Earth's crust. You're not going to form a gold deposit related to granites at deeper levels. That's because pressure controls water solubility and melt. So till you get to shallow levels, you're not going to release a lot of fluid and a lot of gold from a melt. And that's why magmatic deposits form at shallow levels. If you were looking at rocks that had spent their life at deeper levels, metamorphic rocks that were at 5 and 10 and 15 kilometers, they cannot have a magmatic origin. And people tend to ignore that, and I'll get into that in a little bit. So we know when we have a granite at shallow level, if we exsolve a fluid at the top of the granite, we can have a porphyry deposit. Often the deepest gold-bearing porphyry deposits are at 3 kilometers. We can get slightly deeper and have copper-only or copper-moly deposits. And above these, we can have our high sulfidation epithermal gold deposits. And if we mix in some meteoric water circulating around the shallow pluton, we can have our low sulfidation epithermal deposits. That's half of the gold that we explore for on this planet. And just quickly, one last slide to show you what happens. If we take a hydrous magma that may start crystallizing at, say, 4.5 kilobars or 20, 25 kilometers, and it starts rising to the surface. Originally, it may release a fluid that's 58% water or 42% water, 58% CO2, but small amounts. As that magma rises to the surface, crystallizes, starts losing more water, it's not till you get to about 1.5 kilobars or shallower that you start getting a fluid composition that even looks like orogenic gold fluid, which is often 85% water, 15% CO2. And it's not till you get to very shallow levels that you have a total aqueous type fluid, which we see in our magmatic fluids. And you can also see till we get to shallow levels, we don't start losing significant volumes of water out of a granite. So again, because pressure controls water and magma, you're not going to form a magmatic deposit below 3 to 5 kilometers depth. The last slide. This is from Massimo in Switzerland. These are the world-class porphyry copper in orange and copper gold porphyries in blue. You can see the deepest gold-bearing porphyry deposits are only at 3 kilometers to 2 kilometers. You don't form a magmatic deposit below about 3 kilometers if it has gold. Certainly, there's rare conditions. Lundy talks about these, where you can have a superhydrous fluid, magma, which may have 8 or 10% water. But even if that's the case, and you start losing water out of a melt at deeper levels, that water goes, the magma crystallizes inward. The water that is exsolving moves up the mush in between the crystals and doesn't come out till it fractures the brittle top of a magma system. So you're never going to form a magmatic gold deposit below 3 to 5 kilometers. And so that's important to keep in mind. And the last point is that when we look at the global distribution of oxidized intrusion-related deposits, porphyries and epithermal deposits, even though they're responsible for half of the gold endowment outside the Wits, they really form 2 belts around the Circum-Pacific and the Tethyan belt from Southern Europe all the way down to Yunnan and Tibet, China. They can be in Andean arcs, which are continental arc. They can be in oceanic arcs, such as the Southwest Pacific. The key to this distribution is those are the young arcs on our planet. These type of deposits form at shallow levels. They get lost to erosion very quickly in 50 or 100 million years. That's why you're not going to look for intrusion-related deposits through most of Africa, because you're looking at rocks that were down at 5 and 10 kilometers and would have lost their endowment in intrusion-related deposits. So, see here. We are more confused, though. We understand intrusion-related deposits. We understand porphyries. We understand epithermal deposits. There's more confusion when we talk about other gold deposit types. Some of the confusion is deposits like Carlin-type deposits, or these very rare reduced intrusion-related deposits that are in tin tungsten provinces. For instance, Carlin deposits. Here's a model that was in Economic Geology 100th anniversary volume. You have surface water, you have metamorphic water, you have magmatic water, you have mantle water. All these could be in a Carlin deposit. They can't be wrong with their model because they have every type of water known to man. But how do these really form? We have a great exploration model in Nevada for this deposit, where it's a significant producer. But unlike epithermal, porphyry, or orogenic gold deposits, they're limited in their global recognition. So we don't have good global models for these deposits that are not common. For porphyry deposits. We have porphyries thousands of places around the world. And so we have a good global exploration model and genetic model. We don't for rare deposits. Also for more deeply formed deposits like orogenic gold that may form at 5, 10, 15 kilometers. All sorts of different models because we don't know the source area. It's down below the surface. These gold deposits have formed from water coming into large fault systems, moved up those fault systems, formed the deposits. So they're more controversial. And so we know a lot of features about orogenic gold, but today we still have a lot of controversy. If we look at the spatial distribution of orogenic gold, it's much different than the magmatic deposits. It's on every continent of every age. We can look at the youngest deposits. They're tertiary and Mesozoic in age. They run from Nome, Alaska, down to the eastern Cordillera of Colombia, and from eastern Russia to the South Island of New Zealand. Great Paleozoic deposits, especially all through Central Asia, including the world's largest orogenic gold deposit, Muruntau in Uzbekistan. We can look at Paleoproterozoic deposits, such as Homestake here in the middle of North America. We can look at these in northern Australia. And we can look at the Paleoproterozoic deposits, the Great Belt of West Africa, which some of these deposits now have rifted away and now sit on northern South America. And then, of course, all the late Archean cratons have orogenic gold, whether it's central Canada, whether it's Brazil, whether it's many of your Archean cratons throughout Africa, southern India, or Western Australia. So a much different distribution than the magmatic type gold deposits. If we look at the temporal distribution of orogenic gold, remember we said the intrusion-related gold deposits formed in those couple of belts, the Circum-Pacific and Tethyan belt, or at least they're preserved there. If we look at equal endowments between the two groups I mentioned earlier, intrusion-related and orogenic, the endowment is the same, but the time distribution is different. The orogenic gold deposits are well preserved back through geologic time, whether it is Paleozoic, Paleoproterozoic, Archean. When you look at those older deposits, they're almost always going to be orogenic gold deposits. Almost all the endowment in the shallower intrusion-related deposits is preserved in tertiary or latest Mesozoic settings. When we look at the endowment versus crustal growth, we see that the late Archean and the Paleoproterozoic orogenic gold deposits, which are roughly half the orogenic gold that we know of, formed in two times, late Archean and Paleoproterozoic. There may be some older examples, but those may have been eroded away. But about 50% of our orogenic gold is Precambrian age, and it formed during the two main events of crustal growth, probably superplume periods in late Archean and Paleoproterozoic, which now make up 75% of the Earth's crust, the interior of the continents. As the Earth cooled, we were able to start subducting plates below on a cooler Earth, below the cratons, and we created the last 25% of our continents over the last 1.6 billion years. And those are those ribbon continents you see, like the Cordillera of North America, or areas around the margin of Gondwana, the oceanic sediments that were accreted around the volcanic greenstone belts and granite gneiss basements that make up the continents. And during formation of that last 25% of the crust, we formed the other half of orogenic gold in late Neoproterozoic through tertiary time. And if we look what this means, these really are also the times when we had a lot of accretion. We were taking new material added to the continents. We were having volcanic rocks added when we form our greenstone belts. since the last 1.6 billion years, mostly sediments on the margins. When all these things were coming together is our periods of supercontinent formation, whether it's Land and Colombia early on, or more recently, Rodinia, Gondwana, and arguments that a new supercontinent is forming today is eventually Russia will dock with North America. And you can note here that Rodinia, there is no orogenic gold, or not significant orogenic gold, not enough even to plot on the endowment here, but we did create new crusts. So what happened then? To form orogenic gold, you need new crust, you need deformation, you need metamorphism of that crust. And basically with Rodinia, these are our cratons, our continents, these round blobs, or Laurentia, Siberia, West Africa, and they are preserved, stable areas through Earth's history. As the Earth cooled, we started accreting these sedimentary belts. The oldest, the Grenville Belt, is when we were forming Rodinia. But these are the oldest sediments added to the continental margins. And they may have had orogenic gold during deformation and metamorphism, but most of those rocks that are Mesoproterozoic and early to middle Neoproterozoic in age have been deformed and squished and uplifted, and we've lost the orogenic gold from those rocks, not just the magmatic gold, but also the orogenic gold, because these are rocks that have come up from 20 to 30 kilometers depth. So that's why you're not going to explore for orogenic gold in rocks that are about 1.8 to 0.8 billion years old. Those rocks have lost their orogenic gold as well as their magmatic gold. So the key thing about orogenic gold, to have orogenic gold deposits, you always create fluid during metamorphism. You always carry gold in those fluids during metamorphism, but you're not going to form a gold deposit unless fluids are focused into large structures, whether it's Archean here, such as Western Australia. You have these large faults, such as the Bowler-Lefroy Fault, which hosts the Golden Mile, the largest Archean orogenic deposit. We can go to West Africa, the Paleoproterozoic. We have Craton, Archean Craton open, closed Paleoproterozoic basins, and on the basin volcanic margins, we have orogenic gold along these large structures that go for hundreds of kilometers, and very young examples such as Juneau here, where we have structure for hundreds of kilometers and large gold deposits sitting on opposite sides of the structure. You need a large structure to focus a lot of fluid. Otherwise, fluids go everywhere. You'll have orogenic gold deposits. They're high grade, but they don't have the tonnage to interest you as an explorationist. I thought I had another slide, but I guess I don't. Examples such as Nome, Alaska, or Klondike in the Yukon. Great placer fields, 20 million ounces in the Klondike, but little veins everywhere because there's no major structure to focus fluid. We want to target structures. We can target second and third order structures off major structures, and we'll see steep fault fill veins and also extensional veins as you go through fluid cycling. You build up pressure, you fracture the rock, you fill that fault with silica and your metals, and then it seals the fault. Then you build up fluid pressure approaching lithostatic pressure again. You have extensional veins. Then you switch back to fault fill veins, and you cycle over and over with 3-5 million years. And so hundreds of these seismic events form these veins over hundreds of millions of years. And not only second and third order structures off a major structure, but fold systems off a major structure where you have movement along the limbs of the fold can concentrate fluids and be good hosts for orogenic gold. This slide was a little out of sequence. This was what I thought was coming up. This is an example from Nome, Alaska. This is the Seward Peninsula, 8 million ounces of gold recovered, some alluvial, some in the adjacent ocean, more than 6 million ounces from the beaches of Nome where it was worked by longshore processes. All full of here, all through this area called the Seward Peninsula, well, we have orogenic gold deposits, high-grade deposits. The largest one, though, produced only 27,000 ounces of gold. Why? Because you need large structures to focus fluid. It's the fluid, the gold is always there, the fluid is always there, but you need the structure. And you need complexity along structure. We look at the Golden Mile in Western Australia. And if you look at the Golden Mile, you can see in just a period of about 10 million years, we had original convergence. We form a compressional regime. We have a fault fold system. Here you can see the early sort of D1 structures. Then we had a sinistral strike slip event that opened up second and third order features that formed the giant east lode system and west lode system. Then we had more compression and we had thrust faults forming. And then we had to change the dextral strike slip. And we formed the Mount Charlotte ores, which are right over here. So the more complex, the better. If you have a simple geometry, you're not going to move a lot of fluid. Complexity moves fluids in open spaces. You want to look for bends in these long faults that go for hundreds of kilometers, because those are dilational zones. Fluids will flow where you have space. It's common sense, and that's where you'll explore. This is an area I was working in central Lapland over the last 6-7 years. This is the Kitla mine, the largest deposit in Europe. This orogenic gold deposit is about 8 million ounces. And where there's a 20-degree bend in the major structure is where the gold is located. And you can see this all around the world. You want to look for changes in strike and even dip on major structures, and that's where your ores will be concentrated. Much of this, where you have these dilational zones, often there were contacts between units. We can look at Western Australia, Western Africa here. We can look in the Ashanti Belt, and we can see on one side here we have metasediments, on another we have metabasalts. You can see the bleaching of the metabasalts, and the gold sits where we have a shear between the two units. So we can go over here to the Paleoproterozoic. Again, that Kitla mine I was talking about in Finland. We have two tholeiitic volcanic units. In between, we have Biff and argillite, other clastic rocks that shear, and that's where the mineralization is located. Even if you're in concealed areas, using your geophysics to look for contacts between rocks are critical, because you're looking for areas of movement, and most orogenic gold deposits, that movement is sitting between units. That's where your second and third order faults are located. In addition to structure, you want to think about metamorphism. As I mentioned earlier, most orogenic gold deposits, such as in the Yilgarn of Western Australia, Superior Province here, Tanzania, where we just were in Zimbabwe, West Africa, sit in green schist facies rocks. There's very few in subgreen schist. Some are at the green schist amphibolite boundary. But you want to think about metamorphism. Some people argue, well, how can these be related to metamorphism? As I'll tell you in a little bit, they are real products of metamorphism, but they always post-date the metamorphic cleavage. They always post-date their metamorphic host rocks. Why? Because metamorphism in a orogenic belt doesn't happen at the same time everywhere. You're continually subducting or underthrusting material that's being heated while parts of the belt are uplifting. Those parts were metamorphosed early, so you're creating fluid at depth. That fluid moves up during seismic event, fractures the rocks, may move up a kilometer, 2 kilometers, and be deposited in rocks that have passed their peak of metamorphism 5 or 10 million years earlier. But that doesn't say the fluid isn't a metamorphic fluid. It's just produced during metamorphism and moving into rocks that were metamorphosed previously. And another reason this happens is because most orogenic gold deposits form after the peak pressure of metamorphism as rocks are uplifting. Because as rocks are uplifting, you're reducing lithostatic pressure relative to fluid pressure. So all the metamorphic fluid and pore spaces can start cracking the rock, moving into small fractures, larger fractures, and eventually horizontally into those major faults, because that's the pressure gradient, because where those big faults are low pressure areas. So metamorphism and structure is important. And then we want to think of traps. We can think of physical traps or chemical traps. If you have a brittle rock here, like a granite sitting here in phyllite, here you can see a mine added for scale. It's a major intrusive body. You can see how 95% of the ore sits in this competent intrusive body. It's very brittle. Brittle rocks fracture, they open space. That's what we call to be a physical trap. Similarly, gold moves with sulfur in these fluids. This is the Homestake mine in North America. We have a bunch of Proterozoic units. Fluids are moving up the fold limbs, but you can see how all 40 million ounces of gold is in this one unit called the Homestake Formation. It's a banded iron formation. It's iron rich. This is what we call a chemical trap. The fluids hit the iron rich rock. The sulfur reacts with the iron. We dump out pyrite and arsenopyrite, and the gold that is moving with the sulfur also drops out. So we have to think about structure, metamorphism, and physical and chemical traps when we explore for these type of gold deposits. How do we get the fluids moving? This is an example we saw in Juneau way back 35 years ago. It's been seen everywhere, all the way up to the Middle Archean in the Barberton Belt here in South Africa. Changes in far field stresses. That leads to uplift. That gets everything rolling. Here in the Juneau area, we had compression up to 56 million years ago. We had a change in plate motion at 56 to 55 million years. That changed. So everything went from thrusting to strike slip. That started the uplift. Metamorphic fluids then were able to move during seismic events up a kilometer or two, forming gold deposits, and then over 50 million years were uplifted 10 kilometers to what we see today. So changes in far field stresses are the ultimate control on forming orogenic gold deposits. We have different types of orogenic gold deposits. They use different names. Most orogenic gold deposits look like this. They form at what are called mesozonal depths, areas where we have both brittle and ductile deformation. Often that is, some people say 5 to 10 kilometers, 7 to 14 kilometers, somewhere in the range. And most of these look like these laminated quartz veins. They can be shear related. In a more brittle rock, you'll see hydrofracturing, you'll see breccia, you'll see stockworks. When you get deeper down and form hotter orogenic gold deposits at depth, they'll look like this. You won't have the quartz veins, but you'll have massive silicification with the gold. Some of the deposits we just saw in Zimbabwe are like this, because at greater depth, rocks are more ductile. And so they slide, and you don't build up the big pressures that you build up in the mesozonal area. And you need big pressure drops to get silica out of solution. And that's why you see these big quartz veins at shallower levels. But where you don't have the big pressure drops, you don't have the big quartz veins. So deeper orogenic gold deposits look like this, just sheared rock without a lot of brittle features. And the shallowest orogenic deposits that form at 3, 4, 5 kilometers are stockworks and breccia, like you see here. So different styles, depending on different depths of formation. The shallowest of these, I said, can form at 2, 3 kilometers, but where that same fluid cools and gets near the surface, you can deposit stibnite, or at very shallow levels, cinnabar. If you have cinnabar, you still may be 2, 3 kilometers above a gold deposit. But if you have massive stibnite and you're right at the surface and you have some anomalous gold, you may be sitting at the top of an important orogenic gold deposit. Antimony isn't just in epithermal ores, it's very important in orogenic ores. And a good example of this is Donlin Creek, Alaska. When I first went out there, it was just a stibnite occurrence with anomalous gold. Now it's a 40 million ounce epizonal orogenic gold deposit. Similar to the world's biggest orogenic gold deposits, Muruntau in Uzbekistan, Kumtar in Kyrgyzstan, here in southwest Kyrgyzstan. All these antimony deposits were mined by the Russians for their nuclear projects, but they never looked for gold. These are going to be shallow epizonal orogenic gold deposits. They're great targets. So antimony is really important in shallow orogenic deposits. And today with critical elements, critical minerals, even more important. Support for a metamorphic model. If you actually take a laser and look at the off fluid, you will see in the vapor bubbles, not water vapor like you see in a magmatic system. You'll see carbon dioxide, nitrogen, H2S, and methane. Those are the exact same fluids, exact same volatiles a metamorphic petrologist says, oh yeah, we always see these in green schist facies rocks, not even connected with water. This is what a metamorphic fluid looks like. You devolatilize a rock, you create a metamorphic fluid. It has H2S, so it's always going to carry gold. Where does the gold and the sulfur come from? Well, if you take a rock like a shale, it may have 10 ppb gold. That gold's not in the feldspar, it's not in quartz, it's not in mica. It's in those opaques you see under the microscope, those diagenetic pyrites. That gives the rock 10 ppb gold. Those pyrites, though, may have 600 ppb gold or a part per million gold. So when you heat the rocks from green schist to amphibolite, that pyrite converts to pyrrhotite and loses its gold and loses its sulfur. And at the same time, other species like chloride are breaking down, and you lose a lot of water. 3 to 4 volume% of a rock changes the water during green schist to amphibolite metamorphism. That's a hell of a lot of fluid, and that fluid then forms your orogenic gold deposit. A lot of metamorphic models. One of the best, I refer to Ian Pitkin's model here on the Otago schist on the South Island, New Zealand. Ian looked at rocks in the schist that underwent different metamorphic grades. These are gold deposits that host these metals. And as you go up metamorphic grade, mercury, gold, silver, tungsten, antimony, arsenic, everything that's enriched in the deposits get depleted in these rocks. They're moving out of the rocks during metamorphism into that fluid, moving up and forming those deposits. And as you break down chloride and biotite, you create a hell of a lot of fluid, and you're also breaking the pyrite down to put the metals into that fluid. And so that's part of any regional metamorphic process. You create the right fluid to form orogenic gold. The key is having the structures to focus it, to have deposits that you guys would want to explore for. One model definitely does not fit all. You know, you have to study the geology and tectonics of your own belt. Where I've worked in Alaska, I've seen area where you have crustal thickening, hot rocks over cool rocks, heating those rocks, metamorphosing the rocks. I've seen extension and slab rollback and hot mantle coming to shallow levels and heating the rocks. I've seen a slab window where you have 2 plates pulling apart and you add heat in there. You may have contact metamorphism. You may have plumes. The key is taking an oceanic rock and for the first time heating it through the green schist amphibolite boundary to produce the right ingredients to form orogenic gold. So there is not one model. It's a metamorphic model, but there's many ways to do it. And every belt is different. Questions are, why are deposits so large? You want to look for weird stuff. Muruntau is the world's largest orogenic gold deposit. There's an incredible jog in this east-west fault of Central Asia. This fault goes for thousands of kilometers, but where this jog hits, and you could see it on the map, it sticks out like a sore thumb. There's a number of splays off it, and Muruntau and other deposits sit where this incredible jog is. Also, the north side of Muruntau, there's a carbonate sequence. You normally don't see carbonate in active margins. They're in passive margins. But this is a piece of Siberia, that carbonate that broke off collided with Central Asia, and then other clastic terrains sit to the south of it. Carbonate is very weird in these environments. It could be very permeable. You could have karst type topography. Maybe that's important. The Russians argued that these sediments adjacent to Muruntau had a background of 100 ppb gold. That's a heck of a lot of gold. Maybe that's real. Maybe that instead is distal alteration of 280 million years rather than 500 million year old gold that's pyrite that's diagenetic. Who knows if that is really the background of these sediments? Maybe one of these is important, maybe all three is. But for looking for giant deposits, you want to think, what is unusual? And anything weird, anything complex is a good thing. And why is a province like West Africa so gold rich? The West Africa gold fields formed when you broke up that Archean craton. You can see some Archean gold in Liberia and Sierra Leone, but then it came back together and it closed these interior basins that had lots of organic material. You see this carbonaceous material in all the deposits in West Africa. Lots of carbonaceous material, has a lot of diagenetic pyrite. It incorporates lots of gold and sulfur. And so it's a very favorable environment. And that's probably why West Africa and many of these other Paleoproterozoic deposits, where you broke apart cratons and closed them again, have a lot of gold potential. Now, a lot of the confusion in literature reflects our changing definition of orogenic gold since I started. When I started, orogenic gold was thought of as high-grade, low-tonnage type deposits. And these were the 25 largest orogenic gold deposits in the world 40 years ago or so. Today, these are the 25 largest orogenic gold deposits. We're mining these at high tonnage, much lower grades. They were mining them at the grades of some of the gold-bearing porphyries in the world. So both of these deposit types are now being mined at very high tonnage, low grade. In fact, the largest gold deposit, 20 million ounces, Morro de Oro in Brazil, orogenic gold deposit, they're mining at 400 ppb gold. That was a distal geochemical anomaly when I started working in gold, and now it's the biggest gold deposit in Brazil. So other things like sustainability and helping the local people and environmental issues are more critical today in getting a mine going than really the grade. You want the tonnage, it's a big investment to open a mine. So you want a big tonnage type operation, and you generally need that in an area where you can have sustainable issues taken care of. But then some of the problems are, when I started, I would go after something like this vein system here, over here on your right. And we would say, yeah, that's an orogenic gold deposit. But now as they mine low grade, which may be distal alteration to a shear, or there may not even be big quartz veins, they mine this pyrite and arsenopyrite. This rock as a whole might have 600 ppb gold, but they're mining it. And an academic comes out there and says, oh, I don't see a big quartz vein. It's a Carlin deposit, or it's intrusion relief. But then you look, these rocks were at 6 kilometers. You look and there's no granite nearby. There's no carbonate to make it a Carlin deposit. But that's what's led to some of the confusion in the literature. We're mining lower grade material that things aren't as clear as they used to be. And you have to look at the geology and try to understand what's happening in your belt. People like to talk about deprecipitation mechanism. There's never deprecipitation mechanism. Basically, drops in pressure drop out the silica. But as you can see on this upper diagram here, no matter what the pressure is, gold solubility stays about the same. So you lose the silica, but that's not getting the gold out of solution. When gold is moving with sulfur rather than chlorine, even if you drop the temperature, which doesn't happen in orogenic gold, the gold solubility is the same. But when the silica comes out, and also when the fluids react with the rocks, and also when water and carbon dioxide separate or become immiscible, or some people call it boiling, different things happen. You're changing the chemistry of the fluid. And if you have a fluid here, beginning its life here, and you say, go into a more oxidized rock like a granite, gold solubility drops. If you go to a more reduced rock like an argillite, gold solubility drops. If pH changes one way or the other, gold solubility drops. If you react with a wall rock, the gold will precipitate out in the wall rock. So all these things are happening at the same time. You're sulfidizing the fluid, you're changing the pH, you're changing the redox, and there's not one mechanism. Pressure gets the silica out, and other chemical changes get the metals out. People talk about paragenesis. It may make sense in a magmatic deposit. Does it make much sense in an orogenic gold deposit where you have just all these quartz and these wall rock ribbons and gold, bits of gold along fractures in here represent pulse after pulse of fluid, maybe 50 or 100 or thousands of pulses of fluid over a few million years. So you may deposit gold, or you may deposit quartz, then gold, then some base metals, then more quartz, then more gold, then more quartz, then more base metals, then some stibnite. So there is really no great paragenesis. When you see people publish paragenesis, it's what's in the polished section paragenesis. But of the vein, it's almost meaningless in an orogenic world. Is there a unique early fluid? Some people like to say, oh yeah, there was a different fluid first. Probably not. If we go to North China, every damn gold deposit is surrounded by a broad alteration of K feldspar and then alteration near the veins, which is more common, quartz, sericite, pyrite, carbonate. We can go to Lapland, northern Finland, and every gold-bearing deposit there sits in a broad halo of albite. We can go to the Abitibi greenstone belt in Canada, and most of the deposits sit in a broad carbonate zone. I don't think in these cases you bring one fluid along these faults from somewhere and then another totally different fluid. Most likely the first fluids that come up react with the rocks, depending on the fluid chemistry and the wall rock. You form these broad alteration halos. That also makes the rocks more brittle. The next pulse of that same fluid comes up, more easily fractures the rock, drops the silica out of solution because there's bigger pressure drops, and then the next pulse of fluid comes out, it dissolves some of the silica, puts your gold along the stylolites, and so and so and so and so. So you may see broad alteration halos of one mineral type, and then the gold will be in those. And you see this, many examples worldwide. People like to say, well, I see late stibnite and tellurides in all these. Must be a late magmatic overprint. It's hard to believe we go all over the world and there would be, you'd form an orogenic gold deposit and then a magmatic system would come in and put tellurides and antimony in late. Stibnite is probably present in 10, 20% of these. Tellurides are present in at least half of these worldwide. There's two ways to get both tellurium and antimony out of solution. You can lower the temperature, which doesn't happen in orogenic gold deposits, or you can reduce the fluid. And you reduce the fluid, you can deposit tellurium, you can deposit calaverite, which is gold-bearing tellurium, etc. You don't need a second fluid, such as shown here, bringing a magmatic metals in there. Certainly it may happen once or twice, but worldwide, why is this happening? Well, if you deposit some pyrite and arsenopyrite, the next fluid pulse comes in there. It reacts with the early sulfides. That helps reduce the fluid. And then when the fluid's more reduced, it gets the tellurium and antimony out. That's why in all these paragenetic models you see, always tellurium and antimony look paragenetically late because they come in after much of the pyrite and arsenopyrite in orogenic gold. Another thing that really pisses me off these days is geochronology. Everybody is dating all these minerals, all these fancy methods, the rutiles, the tinites, all this uranium, lead, rhenium, osmium, and every sulfide. And you get a little vein like here, and they get 5 different dates over 200 million years or 100 million years. Do you really think there were 5 events bringing those same fluids in at different times? How does that happen? It's not going to happen. We should worry that maybe we don't understand some of the changes happening in the isotope systems. So we're losing something in one of the isotopes and something is readjusting, rather than we have all these different gold events. In fact, when you look at these carefully, a lot of these things happen when things are geologically dead and nothing's happening. And then they say there must be a hidden granite down there somewhere. Not the case. We have to think carefully what these isotopes are telling us. The measurements are good, but the isotope systems are resetting. So don't be overwhelmed when you see all these papers with all these dates on this one deposit. It's probably fiction. Are all orogenic gold deposits formed from metamorphic fluids? What about surface water or magmatic water, mantle water? Can those be important? You know, you go out to an orogenic belt and you see, oh, my time's up. Can I take an extra 10 minutes? Okay, if anyone has to go, don't worry. But I'll just like to throw out some other things for 10 more minutes. Any metamorphic belt, part of orogeny is metamorphism and magmatism. So you're always going to have fluids and magmas in the same belt. In many cases, they're Lamphophire dikes associated with mines that have orogenic gold. That does not mean that there's a genetic association. Some belts of the world, the granites are 20 million years older, some they're 20 million years younger than the gold, some they're the same age, some I-type, some S-type, nothing consistent. It's in many cases, magmas and fluids will use the same conduits. They'll come up at different times, but there will be a spatial association because we have orogeny, we have heat. Lamphophires just mean you have a big fault connected to the mantle, and you might have moved up mantle melt at one time, and fluids came in here at another time. Sometimes the gold predates, sometimes it postdates the Lamphophires. So the spatial association does not mean a genetic association between gold and magmatism. As I told you, it can't work for orogenic gold because water stays in melt at the depths that orogenic gold formed at. You want to have magma though? What about the South Island of New Zealand here, or the 8 million ounce McRae's deposit? There's not a granite in sight. This is one metamorphic belt that didn't get hot enough for magmatism, but we have lots of orogenic gold deposits. So it shows you don't need magmatism. It doesn't have anything to do with it. But a great geochemist, Werner Giggenbach, gave the SEG talk in 1992. They said, if economic geologists don't understand the deposit, where it came from, they just like to put an arrow down there and say, there's granite down there somewhere. And, you get all these crazy models like upside down Christmas trees, people hang their deposits off it. Here we got this giant deposit in Alaska, Pogo, these flat extensional veins. They have the magma coming out of the side of the granite. This is all just, people just want to say, well, I don't know how it formed. There must be a source down there, must be magmatism. They have a hard time realizing regional fluids, metamorphic fluids, can form an ore deposit. Muruntau, the world's biggest orogenic gold deposit, formed somewhere at 8 plus or minus 2 kilometers. The Russians had nothing better to do with their money. They put a deep drill hole 4 kilometers down below Muruntau, so at least 12 kilometers. They intersected a small unaltered plug. And all these models come out now and say that's the source of 180 million ounces of gold. You would not lose gold. You would not lose fluid at those depths. And certainly that small plug can't be responsible for the world's biggest orogenic deposit. Another orogenic gold deposit, because there's some granites in the pit, is Canadian Malartic. It's a big deposit that has been well studied in Canada the last 10 years. If you pick up economic geology and look at the papers on it, you'll see it has been called a porphyry deposit, cyanide associated deposit, oxidized intrusion deposit, stockwork disseminated deposit, and orogenic deposit. Which do you believe? what do these other names even mean? Yet all these are in the literature, and especially your students, what do you believe? Are you going to explore for a certain porphyry out here? This is classic along a shear zone orogenic gold, but it just shows you some of the confusion in the literature. I was just a month and a half ago in Colombia. The largest gold deposits in Colombia are part of the Segovia Gold Belt. It's a 160 million year old batholith. And in that batholith, there are 80 million year old gold deposits that form the gold belt. Nearby, there is an 80 million year old batholith, and all the publications by many famous people who I won't now mention say this has to be the source. These are intrusion related. This deposit you see here, which looks like any orogenic deposit. But orogenic gold deposits form along major faults. Major faults move. At 80 million years, this batholith, this is a large strike slip system, was 1,000 kilometers away in Ecuador, not up here in Colombia. So there's no way that this could possibly have any association with these gold deposits. You need to go back and do reconstructions when you study orogenic gold deposits and look at the geologic map at the time the deposits formed, not what you see today. But again, this misleads to a magmatic model. Are there intrusion-related orogenic deposits? No, people like point sources, but you cannot have an orogenic gold deposit formed from a magmatic fluid. More recently, workers in Western Australia and the Golden Maya and the Archean in Canada have pointed out some of these textures in orogenic gold deposits. Very small volume of these, but you see them in the pit and they draw your eyes to them. You look at these and go, these are epithermal textures. And so a number of papers have come out, even in the 100th anniversary in the recent SEG gold volume, saying orogenic gold deposits are just metamorphosed epithermal deposits. That's insane. What you're seeing here aren't epithermal textures. Epithermal deposits on their surface, they're low pressure. These are low pressure textures. So in some cases, when you fracture the rock at great depth, you will get textures that look like this low pressure texture. They don't make up most of the ore deposit, but some of the ore deposit you will see associated with these because of the big drops in pressure when you fracture rocks at depth. But don't consider these to be epithermal textures. I'll skip that for now. What are isotopes telling us? Just basically, just quickly, hydrogen and oxygen isotopes tell us we're looking at isotopically heavy fluids that are only consistent with a metamorphic fluid. Many workers talk about meteoric fluids, though. Meteoric fluids are surface waters, and the reason they say they're important is because they get very low hydrogen isotope numbers that are much lower than metamorphic or magmatic water. But how do they get those? They take the gold-bearing quartz, they squeeze it, heat it, get the fluid inclusion waters out and say, these are surface waters. And they're right, they're surface waters. But 99% of those are meteoric waters trapped during uplift at the Earth's surface. They're yesterday's rainwater. So it's a meaningless exercise. But that's where you hear about meteoric water in orogenic gold. We're getting lots of new data. Much of this data, this is this quartz. All these are secondary inclusions. People squeeze these or heat these. They get rare gas data or strange isotope data and say, see, is a signature that fits in the mantle field or the magmatic field. This is meaningless to get bulk fluid inclusion numbers and try to make common sense of it. But that's where you see some of the strange models for orogenic gold coming. What about mantle? People now are publishing papers saying orogenic gold comes from the mantle. Well, I can go to Western North America and the enriched continental lithospheric mantle stops here. If I go west of it, the 200 kilometers along the edge of North America from California to Alaska, where lots of orogenic gold deposits are, they just sit over oceanic sediment and crust. There's no enriched mantle there. So if you want to enriched mantle model, it certainly can't fit here in Western North America. It makes no sense. How do you get these fluids from the mantle? A lot of recent articles by David Groves and many of the Chinese talk about, these giant deposits forming in Eastern China from fluids coming up from the mantle. If you had water in the mantle, it would melt the rock and form magmas. It wouldn't bring gold up as a fluid to shallow levels and form these orogenic gold deposits. So just quickly to summarize, there's a lot of crap out there. You need to weed through it. If people say there's a direct association with magmatism, ask them how. Ask them to explain it, because I don't see it. People talk about tungsten, bismuth, tellurium. When they see that, it must indicate magmatic metal source. Absolutely not. These things travel in any metamorphic fluid. Calaverite, gold telluride, was named after Calaveras, the town in the California motherlode. These have nothing to do with magmatic fluid. Radiogenic isotopes. Most of these are worthless because they don't reflect the source of the gold. People do lead isotopes and say that lead is, shows that these fluids are from so and so and so and so. But these are low salinity fluids. They carry arsenic, antimony, gold. They don't carry base metals. The fluids come up, they react with the wall rock. K feldspar may be altered to cerussite. Some of the lead may come off. So the lead you see is the lead in the trap area, and measuring lead isotopes makes no sense, but people do it. People talk about many events over hundreds of millions of years. Many of these dates are not meaningful. People say, well, tellurides and stibnite and base metals may look late, so they must have another fluid source. No, we're just reducing the fluids. Epithermal-like textures, you may see some of those. That doesn't mean these are epithermal deposits that are low pressure textures. And there's finally, if I'm exploring for orogenic gold, I'll look at a forearc, a back arc of an active continental margin. I'll look at late Archean, Paleoproterozoic, and late Neoproterozoic and younger rocks. I'm going to think structure, metamorphism, and traps. I know this gold is probably originally syngenetic to diagenetic gold in marine rocks. And I know with a company, I'd be thinking, what about the economics, the politics, the perception? I mean, if the gold is there, even if it's sub-gram, if there's enough tonnage, I can mine it. But I also need to think about investments in some of these things other than the grade of the gold. So I think I've gone over my time and I'll stop there. So thanks a lot.
There is student outside waiting to enter the lecture theater. I would like to everybody thank Richard, and if you have a chance, maybe connect with him now. And thank you very much. Thank you.
Sure. Sure.